G'day folks, Dan from Cultivate3D here. This is an Annexure video to complement the already existing assembly video that we have made for the Cultivate3D Elevator naked version. Essentially the only difference between these two products is the enclosure, but there are still some differences of the enclosure or the enclosed version and the naked version, and I'm going to take you through those differences first of all, so that the people that are assembling the fully enclosed version, I guess, know where they need to change things, or at least know what they need to do. And also to highlight the changes that we have made since our original Kickstarter prototype of this particular unit. There are a number of those changes, number of improvements. None of them are improvements that have affected print quality in any great degree, but we feel that they're all necessary improvements to improve the overall reliability and structure of this unit, and I'm going to take you through all of those today. So for anyone that's actually watched or seen any of the photos of our fully assembled unit, you would probably recognize what you're seeing right now as an elevator fully enclosed. Just bear with me for a moment. I'm just going to unhide some panels here, specifically the left panel. Now you can see over here, it's sort of perhaps a little bit hard to see, but I've just highlighted what the naked users would identify as the naked left electronics enclosure panel. It's not only an electronics enclosure panel, but it also braces the left side of the printer to the front side of the printer, I guess, through its shape. Now, I have left some of these panels visible in this rendering, if you like. You can see these panels on the corner. So people that have watched the naked video would recognize these corner braces as they're known. There are 12 of them in the naked version, and they're all over the corners of the printer, and essentially they're there to make the printer more stable. Now, obviously, if you've got an enclosed version of the printer, your left and like electronics enclosure panel looks more like what you can see highlighted in red here rather than what you can see highlighted in red here. So I'm hoping you can see the difference there. The difference isn't really a lot, other than, of course, the number of screws that need to go into this. And the fact that you fully enclosed version people have an aesthetic panel that fits on the side here. We call it a left fascia, which is really only there to look cool. There's no real purpose. It perhaps strengthens the position of which you insert the spool holders, but otherwise it has no real other purpose. It's an aesthetic component rather than anything else. Now, these screws here along the aesthetic panel, for those that are building the fully enclosed version, are M3 12mm screws as opposed to M3 10mm screws, which go across the area, the parts of this panel that don't have a fascia on them. So if you could just remember that throughout the build, you'll see they won't be long enough. If you try and use the M3 10mm screws, they just won't fit. We've included enough of the M3 12s for you to be able to assemble this component. And on the back side of these screws, as you've probably already figured out, will be M3 3030 hammer nuts, as opposed to over here. Well, in fact, they'll all be M3 3030 hammer nuts, because anywhere that you can see that we're installing an M3 screw into a 3030 extrusion, we're using M3 3030 hammer nuts in that part. And for those with a fully enclosed printer, you will have extras of those. All right, so going through some of the major differences, let's just start specifically for owners of the fully enclosed unit. You could probably skip through. I'll try and add notes to this video. For those that have the naked version, you could probably skip through this part right now, but let me just highlight the changes that have been made for the fully enclosed version. Primarily, as you can see, we've got all these panels. You can also see that we have handles on the front of the front panels. These are, I believe, M4 screws of about 10 mil length. On the front of the handles. You'll know if they're not the right length because they won't fit in. You can also see that we have hinges over here on the left and the right. We also have a separate panel here for the fully enclosed, which essentially spaces things out. The naked version customers will not have that separate panel. The naked version customers will not have these the left-hand side panel, the square panel. And of course the fascia which fits over the top of it, and of course the same thing with the rear panel. So although you can see these corner braces, the fully enclosed customers will not have corner braces. These acrylic corner braces, as you can see, highlighted right here and here and here, etc., etc. So from a side panel perspective, that's the main difference. From a top door perspective, there are a number of big differences. And first of all, let's just get through to the glaringly obvious one. Naked customers do not have hinges over here. You do not have a top door. Okay, it's an open unit, and because it's an open unit, the extruder rail assembly fits down a little bit lower, about 20 mil lower. It actually like attaches to this 30-30 extrusion which comes along here, rather than attaching to the 20-20 extrusion that our fully enclosed customers will have. There is also an extruder panel or an acrylic panel that the naked version customers will have, that basically gives this cable chain something to run along without sort of flopping into the print. It performs almost no other function than that. So you know, that's probably about the crux of the major changes. Now, as I've already mentioned, anything that fits over here for fully enclosed customers, anything that fits into a 30-30 extrusion and goes through a 4.5 mil acrylic panel, will use M3 10mm screws into M3 30-30 hammer nuts. Okay, so M3 10mm screws, M3 30-30 hammer nuts. However, over here, where they go through into the fascia panel, they're M3 12mm screws going into M3 30-30 mil hammer nuts, or sorry, 30-30 hammer nuts. So again, naked customers will not have to worry about that. We do not have fascia panels. So for example, if you are a naked customer, these screws here, 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 etc. Are all going to be M3 10mm screws going into M3 30-30 hammer nuts. All right, so pushing forward, I think it's pretty obvious. If you've seen any of the assembly video, you'll understand how hammer nuts and screws fit together, and I guess in general where they fit together. So let's start getting into some of the major differences from, or at least the annexures, the bits of design that have changed since our original assembly video. Now, just to explain the complexity and difficulty of making a video of this type, or at least of our original assembly video. When we do this, everything happens sequentially. When something changes, then we kind of need to change everything throughout the entire video, as in every single change needs to basically involve an entire redo of the video. So the purpose of this annexure is to try and save us time. It allows us to manufacture your products quicker and get them out to you quicker, and also to make it at least cheaper for us to operate. COVID has been an absolutely horrible situation for us as 3D printer manufacturers, especially of large niche products that are specifically sold into the aerospace industry. Our industries have been screwed. I've taken more cancelled orders in the last 12 months than I've ever taken in my entire life, and specifically because, well, when factories can't social distance and people have to work from home, things that require you know, people working together, like assembling kit build 3D printers, tend not to happen. So yeah, look, it's been difficult for us, and really our main focus is getting you your products in as high quality as possible, as quickly as possible, with as little screw ups as possible. And part of that involves not redoing work where a simple annexure could suffice. So hopefully that's got that out of the way. All right, let's get right into it. First of all, this is for everyone. This is for owners of the naked version printer and, of course, the fully enclosed printer. I'm just going to hide this rear panel. All right, so this should be a little bit familiar to those that are assembling or have assembled the naked printer, or at least seen that video. Right over here, I'm just going to zoom into what we call, too far, to what we call the front lower Z idler. Okay, now what we've got here is a belt which comes across both of these pulleys. This one here is a smooth pulley. It's a smooth GT2 20 tooth, no teeth pulley, and this one here is two front face-to-face F608 ZZ bearings. Now, as you can see, as per the previous videos, the belt runs in almost exactly the same way. However, this particular part is different. So, most importantly, over here, instead of having two F605 ZZ bearings face to face, we actually have a proper idler here. This is an M5 bolt. Through the M5 bolt goes a, I think we have a washer. Perhaps not. We have the M5. We have the GT2 22 no tooth idler, followed by a washer over here to create some sort of face for everything to tighten against, followed by, as you can see, an M5 3030 hammer nut. Now, in fact, there's a little bit more to it here. We also have an M5 nut here to sort of hold this assembly in place and to allow us to tighten this thing together. Now, what's really important with this particular part of the assembly is that this particular part and this particular part are not tight together. Okay, really all that this nut is doing is allowing these three components to really tighten together to each other. This should not be tightened to this, so the nut should not be tightened to the idler, and the idler should not be very hard up against this M5 screw head. If they are, you'll find that you destroy the inner bearing of this component, and this component doesn't work too well. The Z motor needs to work too hard. Now I'm just going to disassemble this component right now just so that everyone can see what's going on. Let's just start by using the tweak component or tweak command. Come on, what are we doing? We're moving apart. Okay, so first of all, we have an M5. I'm thinking that's a 25mm nut. Screw. Followed by our idler itself. Might need to select a few different components of this idler because it doesn't look like they've been grouped together. Hopefully they all come in one piece. No, they didn't. Well, you can get the picture. It's not important. We'll just leave those bearings there. Followed by an M5 nut, which is about to come out. And really, this is how I want it assembled. It does not matter if there is a bit of slack in between the head of this screw here and the nut here, followed by a washer. Come on. And then screwed into an M5 3030 hammer nut, as you can see here. Ignore these bearings here. I could have pulled them out. I'm not going to bother for the moment. All right, so you can see how this component is assembled. Essentially, this should be able to spin freely. There should be almost no friction on this component here. If you've tightened the whole thing together and you cannot spin this component here, you've tightened probably this nut against this bearing, or at least this this eyelet, too much, and you need to go back a few steps. But you should be able to tighten that in with this M53030 hammer quite effectively, and it should create a very solid, stable component. Right, so now let's have a look at the front idler. Okay, the front Z idler. Now this one's a little bit different, again, from the documentation. We had this crazy, complex arrangement. The feedback that we had from an unnamed space exploration company said that it was just too dicky, basically. They didn't like the assembly that we had, so we simplified it. We simplified it by basically making the bolts thicker and getting rid of some of the over-complex parts, and this created the rigidity that we needed. So I'm just going to tweak these components out, and I'll try and do this in as painless a possible way so that you guys can see exactly how this part is assembled. So it won't be a moment. So as you can see, we have an M5, I'm going to guess 25mm screw. I don't have those details on hand literally right now, but I'll add those. It is a 25mm screw. We have, following that, on the inner face of this component, we have an M5 nut, much the same as that is an M8 screw and an M8 nut. Sorry, not M5. My sincere apologies in that regard. So an M8 25mm screw and M8 nut, and as you will see over here, we have an M8 T-slot nut. There should be 6 of them included in the fully enclosed units. There should be 2 of them included, at least 2 of them included in the naked units. Now, this nut specifically is one that you need to worry about early on in the process. You need to slide this nut in early. It needs to go in when you are assembling the frame. If you do not do that, you'll need to pull apart the frame to some small degree, i.e. the 3D brackets, these 3D brackets, in order to fit them in. It's not the end of the world, and I have done this myself. If you do happen to screw this up and don't put this nut in at the start, it's just really a matter of loosening this grub screw right here and a few of the other bits and pieces to be able to pull the frame apart, to be able to slide this nut into place. But it is very important, if you can, it'll make your life a lot easier, to put this in at the frame assembly stage, which is very early on in the process. I will add subnotes to the original assembly video to get you to have a look at this annexure when that occurs. All right, so all of that screws in together, and it should tighten nicely to the frame and create a very rigid component which will not flex to any noticeable degree or negative degree when this belt here is placed under tension. And this belt here will be placed under more tension probably than any other belt in the entire assembly. Now bear in mind, this will be repeated for both the left and right sides. So you're doing this on both sides of the assembly. So that's the first change, okay? That's a big change because we had an over-complex, really finicky part that sort of was braced on one side and had a whole bunch of very silly things happening. That has not occurred anymore. We've strengthened this bolt here. That gives us a lot of additional support to be able to handle the very tight belt that we have over here, and the same thing with this one over here. It is really just it's a simplified part, easier to assemble, and should at least make the assembly process just a little bit less painful, and it will be a painful process. You know, this is a big 3D printer, and there are 175 individual component types and probably thousands of different parts. So we try and make it as painless as possible, and my apologies if anyone feels like killing me at this stage. I do not blame you. So glaringly obvious right now is what we've got right here, as opposed to the original assembly video. Not only will our naked and enclosed customers, of course, have these side panels, or for the naked customers, these corner brackets, we have now included these 30-30 corner brackets on each and every in each and every printer, and that goes for both naked and fully enclosed. Now these corner brackets go here, There's another one here. There's another one over here up the top as well on the left and right. However, you will notice there is none here and none here, and the reason being is that we have L brackets over here and here. They're not really required, and quite honestly, once you have this unit assembled with the side panels and these components, they're rock solid. It's the most rock solid assembly that I think I've possibly ever seen, really. Like, you can lean on this thing and it doesn't move. It is a very solid assembly. So this is one thing that you can add, you can retrofit add. If you get to the end of the assembly and go, I haven't added them, we'll just stick them in there. It's a fairly easy process. Another big change, and this one goes for both naked, well, big change, I'm going to say small change, but it's really about making things easier, cheaper, and less expensive for us to manufacture, and of course quicker to get out, is that we used to have this weird assembly with a 20/20 corner bracket here, to which a nut went through. It was impractical, it was silly, it was foolish. Really all it requires is taking off the bottom link of one of your smaller cable chain assemblies, and if you do need to, drill out the hole and stick an M5 screw, and I believe that's an M5. Let me see if I can figure it out. It looks to me to be about an M5. I'm going to say 25 mil. 25 mil. It is a 25 mil screw through to another M5 3030 T-slot nut going into this extrusion here. And basically what that does is it gives us space for this bracket here, and it also removes one of the less necessary components, which was a 20/20 bracket that we had it going through prior. So should make things a little bit easier, a little bit more sturdy. Over here up the top, everything sort of fits together the same as the rest of the assembly. Now, one thing that you guys may have picked up on is this weird 3-screw arrangement that we have happening here. Now, one of the biggest pieces of feedback, biggest points of pain for our unnamed space company during assembly was tightening this particular belt. Personally, I didn't understand that. I found no problems with that, but after a few months of usage, I started to find that what I thought tight belt, you could actually start to see a little bit of backlash developing, especially on certain movements of the Z-axis, and that backlash was basically, it was a matter of the belt being tight on one side and loose on the other. So we needed a way of tightening this, and our particular space company that assisted us with the development of this product, they even submitted to us various designs for this, which we just plain rejected because we knew they would take too long and be too expensive to manufacture. I think we've come up with a better solution. It's easier, it's simpler, it's more robust, it will not melt in hot environments, and essentially it's a 3-screw arrangement. So what we now have is well, first of all, nothing has changed here in this front Z rear, the forwardmost Z rear belt attachment point is exactly the same. You essentially stick in an M5, I'm going to call this probably a 50 mil screw, maybe a 45 or a 35. See if we can find that out. It's not telling me right now. Whatever it is in the documentation, you really don't need this spacer here. There's a nylon spacer that we've put in here, and it's been documented to put it in there. I don't think you need it. There you go. It's a 25 mil spacer, nylon spacer. You do not need that nylon spacer. You can just stick in the screw. Add to that what I would recommend, and this is probably important just to highlight. Anytime you are inserting an M5 screw into a 20/20 or 20/40 extrusion, such as make a slide, I highly recommend that you do not use hammer nuts to do so. We've included enough ample amount of flat T-slot nuts that are similar to the type that you can see here. The beauty of flat T-slot nuts is that you do not need to make sure they have rotated correctly into place. You just screw them in and they will lock into place perfectly. So we recommend that as one of the changes that you no longer use this older style of hammer nut in a 2020 channel, that you use this newer style. Okay, this is newer for us in terms of the way we've documented it. We recommend you use these both here, and, well, you can't quite see it, but on the inside where this screw fits in. Now, the tensioning system. Tensioning system is pretty simple. In fact, it's as simple as I think that we could possibly make it, and trust me, we've spent a lot of time thinking about this and mulling over various ideas, including those sent to us by various engineers. Okay, so what we've got is basically a belt which is attached to this screw essentially here. You could use cable ties here, or we recommend using cut in half a GT2 crimp. We've included about 6 of them in each kit. Cut them in half, that'll make 12. So you would either have a crimp here or use cable ties if that's what you prefer to do. Cable ties are easier to work with. So attach that around this one here. Over here, make the belt as tight as you can reasonably make the belt, and attach it to this one here, but leave a big loop, because if you leave a big loop, you'll have space to stick a screw in combined with one of these T-slot nuts, not one of the hammer nuts that you can see here, combined with a T-slot nut, and you can actually angle that up, and by angling it up, what you're doing is creating a larger area in this space here of this loop, and therefore tensioning the belt, and hunky-dory, you now have a drum type Z belt that will not need to be retensioned. They should all be steel core belts, and with the amount of tension that this scenario creates, you will find that you will not need to retension them after a certain amount of hours. It's going to be a very tight scenario, and certainly if you do need to retension them, all that you need to do is basically move this nut a little bit to the left. That's going to create a greater area over here and tension the belt more. To me, seems like the easiest possible solution. It involves the lowest cost, and allows us to keep selling our printers at the price that we do. And certainly, from a manufacturing perspective, does not mean that we need to spend a great deal of time on the manufacturing process. Okay, so moving on, what else do we have that has changed? Let's see. Okay, all right. This has changed. This is certainly different. This is the Z motor. Your motor will be bigger. We just couldn't find a NEMA 23 motor model that was of the correct size. But whatever the case, this is a NEMA 23 motor represented with a NEMA 23 brake. One thing you will notice is that there isn't much happening on the underside of the bracket. Okay, the other one sort of went all around the brake. We actually changed motors, and therefore we needed to change the way that it was braced, but we also needed this brace to be able to be movable up and down. You will see that you have a slot here. Okay, and that allows you to move this brace up and down and basically just keep this motor in a nice, stable, steady position. And we haven't modeled it properly there. We probably could have moved it up a little bit further for representation purposes. You've got a few holes here, but essentially it allows you to make this motor nice and flat. You don't want this motor skewed up or down in any particular direction, and you can see that we've kind of screwed our model to some degree here. I might just tweak that back into the correct position for the purpose of this exercise. Sorry about our poor modelling of GT2 belts. Inventor does not handle this very well at all. Nevertheless, that's essentially what it should look like as it goes around the two pulleys. Nothing much has changed on the front side of the pulley. We've still got a slotted arrangement here. The slotted arrangement really allows you to basically pull this motor up. You want tension in this belt here. If you do not have tension in this belt here, you will end up one day with big scratch marks all over your print surface, because essentially this belt will have slipped, causing the XY gantry to drop into the bed, and it's one of the worst mistakes that you can make, because you're basically going to be looking at a lot of damage to your bed and possibly your hot end at the same time. So we really want this assembly to be as tight as you can possibly make it. It's slotted. You basically pull up against it while tightening these nuts with all 4 of your hands. Get some extra ones, basically, and that will allow you to create a nice solid component there, which will not slip. The other thing which we haven't actually updated yet in this model, and I don't know why, we probably should have, but don't do this. You can't do this. We haven't included these 2 components here. We've included an extra one of these components here. Just stick another one either side of this motor, anywhere out of the way that doesn't conflict with anything. Essentially, this is a dumb idea. We should never have even thought about it. I don't know why we even did. It doesn't strengthen the component. It actually makes it weaker. It adds more mass to these 2 cross members over here. So yeah, just put another one sort of left or right of this. It does not matter. It's not important. So another big change that was requested was that our particular dummy testers did not like what originally happened with these IEC ports. We originally had these IEC ports, which are these little power ports. Usually had them coming out the side of the printer. From an aesthetic perspective, admittedly, it wasn't particularly good look. From a functional perspective, it also prevented us from adding a spot for a second solid state relay, also known as SSR, these 2 things here. So this particular model that you're seeing right now is part of our water-cooled design. I've pulled out a whole bunch of the other water-cooled stuff, but our water-cooled unit requires an enclosure heater. We need 2 SSRs. You will only need 1 SSR unless you're printing with very high temperature materials like PEEK. So yeah, this particular component here, like, you'll only have 1 SSR. You've got 2 holes for them. You can put them up here or down here, whatever makes you feel most comfortable. I'd say probably lower, might sort of maybe lower the center of mass and reduce any case resonance issues. So we'll let you figure that out. It doesn't really matter. I just probably put your SSR down the bottom, even though you've got these holes here. The water-cooled customers have an extra IEC port. Now, what that means is that 2 things. You will have an IEC C14 or C14, if my memory serves me correctly, cables, preferably 15 amp if you can get them, 10 amp if that's what it says on the packet, but make sure you look at the cable, because if it's a skinny cable, just don't use them. Use high quality IEC, at least high quality 10 amp cables or high quality 15 amp cable, or rated 15 amp cables. Now basically what this means for fully enclosed customers is this cable will come all the way along the back. It will go through this silicon piece over here, which actually has a little cross cut out of it. You can't see it. And then come out the back of your printer into whatever multi-port adapter that you've got. If you're a naked customer, you would probably just run them down here, and if it were me and it were on a table, I'd just cut a hole in the table and run the cables straight out of the bottom of the hole, or run them out the back and just over the back of this 8mm rod, or underneath the 8mm rod, over the back of the printer. It doesn't matter. Now your bed will not be coming all the way out to the extent of this. You can't see the bed in this particular model. It's not important. Yeah, your bed will be whatever size fits within this sort of hole here, and you just talk to your local aluminium manufacturer. We recommend an aluminium plate as opposed to its alternative. I can't remember what its alternative is. Aluminium sheet. So aluminium plate is apparently the flatter of the 2 types, and ask them if they can CNC cut them. For us here in Australia, to have a plate CNC cut all up costs about $180 for a 6mm plate CNC cut perfectly to size. There are no sort of notches or holes or anything like that need to be cut through. It's a very, very basic machining process, and just about anyone locally, we found 2 or 3 different manufacturers that can do it. We just picked the guys that did it cheapest, and it cost us about $180 for our entire print surface. So anyways, these 2 cables will run along here, alongside or underneath, if you like, or alongside the build surface, and come out here, or at least come underneath this 8mm rod, and then out the back into a multi-port. So I hope you guys get the point there. You'll see when you get to that stage of assembly of the documented naked build, they were coming out the side. Again, just ignore that. All right, so what else has changed in this? Well, okay, major change that did not actually occur in, well, certainly not documented in any of our documentation. This is a 24-volt system now. You will have been provided with 24-volt switching power supplies. They will accept a 110 to 250 volt input. All right, they are larger than the previous ones that we had originally documented, and they output, of course, 24 volts. Now, all of the fans that you have been supplied are 24 volts. Most importantly, these little 40mm fan over here. We've also got fans on the front of your hot ends. We had perhaps another fan here on the front of the electronics enclosure, which you can see in a sort of exploded view over here. So these are all 24-volt fans, and they will run just fine running out of the fan input, which is, I should say fan output, which is roughly around here on your motherboard. So this is where all the 24-volt fans ultimately get plugged in. There are a few things which aren't 24 volts, and this is another change that we've just sort of opened up the electronics enclosure to show. These little things here, all right, these 2 little things here are called buck converters. Essentially what they do is convert one voltage into another voltage. Now, this was a hard one to document. It hasn't changed. Our servos, the servos in the Medusa system, which you can see right there, these red things right here, these servos work at peak performance at about 7.2 volts. Now, bearing in mind that everything that comes out of this motherboard is either at 24 volts or at 5 volts, we need to convert whatever that is into 24 volts. And the way that we do that is with these buck converters. All right, so these buck converters have a little screw on the top of them. These screws allow you to adjust the voltage that they output. So follow the wiring diagram. We will update the wiring diagram to reflect this, but anyways, one of these buck converters will basically have a 24-volt output, and you will screw this little thing down here until that output reduces to 7.2 or less voltage. Now, the less voltage you have, the further away, or at least the further down you are from 7.2 volts, the less power the servo will have, and probably less reliable it will be. So try and get it to 7.2 volts. So you will have a, in most cases, I believe 24 volt output going down here. Use a multimeter on the output pins. Output pins are, I think they're there and there. And as you're rotating it down, periodically measure the output. Once you get to 7.2 volts, you're sweet. Now, the other one of these buck converters is for those of you that wish to light your internal chamber. We have not included any lights. If you wish to use 12 volt LED strips and stick them across the front here with some of the included retainers, you'll see what I mean at a later stage when I send you some photos. But whatever the case, when you're using a 12 volt LED. They do not run, although they are rated at 12 volts, they do not run particularly well at 12 volts. You will get flickering at 12 volts, specifically when you have a PWM event occurring from the motherboard, they will start to flicker. So the easy solution to that is to reduce the voltage power supplied to them to roughly somewhere between about 10.2 and 11.2 volts. And when you do so, you will find that you get no flickering out of your lights, that they stay nice and stable. You will get them, they'll be slightly dimmer than they would otherwise be at 12 volts, but they will not flicker and will not annoy the crap out of you. So that is really the purpose of this other one. And as you can see, they're just attached with a little screw down here. Now, this one over here has no screw holes. This thing is called a relay. It has no screw holes. This relay, its specific purpose is to turn on and off the Z motor brake. The thing on the back of this. Right, this relay connected according to the wiring diagram. It has no screw holes, so use some double-sided tape, preferably the spongy sort of stuff that you pick up from your local hardware store, and just stick it to the side of this thing. Obviously wire it according to our wiring diagram. Now the purpose of this relay is basically when power is cut to this unit, we do not want the entire gantry dropping to the ground and smashing into your print. Let's just say you have a blackout. This entire component would drop straight down, and it would be a disaster if you have a print occurring. What we want is for the brake to kick in, for it to lock everything in position, so that you can even use things such as a UPS to restore your print without damaging your print, and continue printing as if the blackout or brownout never occurred. So this one here is just double-sided taped to this right side, what we call EE panel, or Electronics Enclosure panel. So I'm hoping that makes sense to you. Certainly, if anyone has any questions in that regard, come talk to us. Probably the most glaring change to anyone, including naked and fully enclosed owners, is going to be this. Now, this was originally a passive component. By passive, I mean Bowden tubes that connected the hot ends to the extruders. So the hot ends, which aren't actually shown in this for some reason, I've obviously hidden them. And just imagine there are hot ends here. We had Bowden tubes connecting the hot ends to the extruders, and literally this X gantry would literally just drag around this component here. Now, that is no longer the case. Why isn't it the case? Well, probably because we didn't think too much or enough when we went and redesigned it. But whatever the case, this motor here is superfluous. This GT2 16 tooth, I'll get to that in a moment, is superfluous. This belt is superfluous. You don't really need it. What used to happen in our original prototypes, the ones that you would have seen in the Kickstarter video, was literally this gantry, this X gantry or Medusa gantry would just drag this thing around left, right, and center. And what we noticed, especially on large prints where it was being dragged around a lot, was you would see slight imperfections in the vertical surface, the Z surface of your printed models. So we thought, how do we get around this? Because what was happening was the extruders were actually pulling themselves always to the right of the printer. They were always pulling themselves towards the filament because, well, there was nothing stopping them from doing so. So we thought we'd be smart and add this extra motor, which we have added. It is in your kit. You can use it if you wish. This extra motor, this extra belt length. We've also got an idler over here, which is a 20-tooth idler. It does not need to be a 16-tooth idler. Attached to two, and I'll just rotate around this one again, to two attachment points, which have now been added to our gantry, right here and right here. Those attachment points, very simple. It's just a screw that goes through with a nut, securing the whole thing to the actual extruder platform itself. And this motor is run in parallel, in direct parallel, alongside this motor over here. And that's the way that it's wired in. Okay, so what you'll need to do is you'll need to literally join the wires parallel join the wires from this motor to this motor here if you wish to do so. There is an easier way. There is a much easier way. And basically, like, what it involves is just preventing these extruders from pulling themselves back down to the spool holders, which would be the wires over here. And that is to just put a big long Bowden tube from your spool to the motors, and therefore they don't pull themselves back anymore. There is no back pressure there. That would still mean that it's a passive system. It would still mean that this X gantry will literally pull things around from the left to the right. Certainly when it's pulling to the right, it will always be pulling and have some sort of back pressure on it, but certainly it won't be doing so to such an extent as it would be if the extruders were always pulling it in the opposite direction. It sort of pulls it, gets it to a certain point, and then it sort of stays around that point within a sort of an X dimension of maybe say 50 mil either side of where the gantry is. And quite honestly, if you do notice a slight imperfection in your Z surfaces because of it, hey, it's 3D printing. We're not talking about fine CNC milling here. We want it to be as accurate as possible, but really within reason. I think my experience, I have not noticed any noticeable difference between just having a Bowden tube between my spool and these motors, or at least my, which you can't see right here, my filament out sensors, which should be attached right here, and the motors. If you have it between the filament out sensors and the motors, it's enough. You don't need this motor. This motor is probably going too far. I have not noticed any noticeable improvement over this simpler solution, which was just to put a Bowden tube, doesn't even have to be connected, just a tube between here and here, or here and wherever the extruder is, will be fine. And I'll add photos of both of these setups at a later stage so that you can see how you go about it. One of them, this motor situation, a little bit more difficult to wire. You probably have to join a few little things over here. It makes little difference. I probably wouldn't. If it were me, I wouldn't. Having tried both methods, there's too much screwing around with this motor over here. It's an extra sort of cog to cause problems at some stage, and it's just not really necessary. The net benefit is very little. So let me see what else we've got here that has changed. Okay, yep, this one's an interesting one, and it's one that should definitely be explained. I'm just going to hide this front door. What have I done there? Whoops, I hidden extruder. Let me try that one more time. We'll hide the front door. All right, so position of this one right here. This will actually look a little bit different for you. I'm not sure why the updated version hasn't come through to this model. But whatever the case, your X, your X end stop will actually be offset down from the actual acrylic part to which it mounts slightly. Now, what I want you all to do is, you can see this metal arm of the X end stop. We'll just try and highlight that a little bit better. It's not letting me. Okay. This metal arm here, what I want you to do is right about here, bend it out about 90 degrees so it's pointing straight out. In its current position, sometimes it won't trigger. Basically, it should be triggering against the servo, but there's a slight manufacturing differences between all of them. Just bend out that metal arm from there, just bend it straight out, and it's going to reliably hit this servo every single time, and you will not have some of the problems that we have had during our experimentation. What else do we need to look at in this one? I'm just going to quickly go through the model. Okay, down here, most of our customers will not have even a space for this third switch. This is really for our water-cooled customers. The water-cooled customers, obviously, This is really for our water cool customers that have heated enclosures. This is essentially a safety switch for heated enclosure. You really won't need that. You're also not seeing the heated enclosure assembly at the back here. Most customers will never need to use it. And if you do, please contact me and I'll be happy to send you the model for the heated enclosure. What else do we have? All right, so let's just quickly go through for our fully enclosed customers what we've got happening different to the naked customers on the top here. This top panel, as you can see, is attached by 2 hinges on the left and right. These are countersunk M5 screws going into, on the top, because it is a 2020 extrusion, an M5 2020 hammer nut. On the bottom, because it is a 3030 extrusion, going into an M5 3030 hammer nut, which fits over the what is now hidden, but I will unhide it. Here, just bear with me. Going over the top of the rear panel and into the 3030 extrusion. And for enclosed customers, just please ignore this unhidden corner bracket. It just goes straight through that into the 3030 extrusion. Now, all of these screws here, as always, if it's a 4.5 mil screw, or sorry, 4.5 mil panel going into a 3030 3030 extrusion, please use M3 3030 hammer nuts for this purpose, and you should have ample amounts supplied, plus 10%. For that purpose, for everyone that loses one throughout the course of the process. Should just say that if you ever run out of anything, just let me know. We'll send some more to you. But please try and be frugal with these things. COVID has made it really difficult for us to even get to this stage. What else do we have? I'm just quickly going through the design to see if there's anything else that really needs to be mentioned. Not a great deal at this stage. Oh, okay, so 2 things. You will notice now we have, as opposed to the original assembly documentation, we now have 2 panels for the top and bottom, and we now have a separate gusset, which you probably figured out before when we were looking at these buck converters. We now have a separate panel which separates the high voltage side from the low voltage side, and the reason we've done that is simply because of safety. You don't want to be dropping screws down into this high voltage side. Certainly while the printer is on, there will be times where you will need to maintain or do something or adjust a stepper driver. God forbid a screw falls out and falls down into this high voltage side. All of a sudden you get a big spark and something blows, and all of a sudden, potential for danger. So we figured we would separate that with a gusset. We've now got a gusset which we've also purposed for mounting these buck converters to, and basically it means that all the dangerous stuff that you can get your electrician to do, and we highly recommend that you do if you are not comfortable with 240 volt electronics or electrical systems. We've separated that dangerous side from the much less dangerous side, but you still need to be careful side up the top here. So and we've done that by 2 panels now instead of 1 panel, and hopefully that will make things just work a little bit better. Another small change, I'm sure you guys will figure this out when you're getting into construction, but your X idler bracket has just been strengthened. You now have 4 screws instead of 3. We've just changed the design of it. We cracked a few of these things during the construction of a few of our prototypes, and we figured we might as well just make it stronger. So it's stronger, it should never move, and hopefully keep everything nice and tight on your X belt, which will create much better prints than something that could potentially work its way loose, and a more reliable system. Other things that have changed, well, you probably won't notice because, well, we actually assembled the Medusa system for you. So although you can't see the hot ends in this particular version, let me take you through all of the changes that have occurred regardless, because you will notice if you're looking at assembling the Medusa system or disassembling the Medusa system, that we have made changes. First of all, we had to raise up our X cable chain, and by doing that we've used a few spaces here We've used another component here, which fits into the rear Medusa acrylic plate. That's all screwed in with the 3 screws that you can see there, there, and there. It goes through the spaces, and of course nylock nuts on the underside just to keep things nice and reliable. The whole thing is fit in a very similar manner to before, just using a captive nut and screw. To the Medusa system itself, not a lot has changed, I do not believe. I think we've still got our sort of 2D adjustable brackets here. You adjust these brackets according to your nozzle positions. You may change nozzles, brands of nozzles, etc., and need to adjust these from time to time. Specifically, we have not included and do not recommend that you use. We do not recommend that you use nylock nuts here and here. On the front, here, here, and on the back, here and here, we have included enough M3 star washers to prevent the need to use nylock nuts here and here. And the reason for this is simple. It's just a pain. If you need to adjust these, you just want to be able to sort of maybe apply a bit of firm pressure to these screws, or these nuts, on the back, and screw on the front. When you've got to pull out pliers, and then it just becomes difficult and a pain. Now, for the same reason, we have also done the same thing and recommend that you do not use nylock nuts on the rear side of here. In fact, we recommend, unlike the documentation clearly, we recommend that you go screw, spacer. This is an aluminium spacer. You can't see it here. I don't know why we haven't got it in this particular model, but another star washer on the front here. You'll see it in the assembled ones, followed by go through the acrylic component, another star washer on the rear side, and do not use nylock nuts here. Right, again, this is another one of those components that you just want to be able to apply your finger firm pressure to this nut at the back, while tightening with a screwdriver at the front to lock it into position. Having to get out an extra set of pliers while you're trying to juggle with that, it's just too difficult, and we found this to be a very reliable solution to adjusting the position of these vertical adjustment stops, these 2 vertical adjustment stops, to which the rotator uses as a physical stop to make its positioning accurate. Now, one other change that I can think of right now, probably a little bit harder to pick up in anything else that we've done, right here, we have moved the Z Max Endstop, which you do not need if you are a naked customer. But if you are a fully enclosed customer and have a fully enclosed unit, it would be a good idea to put this one in position. Now let me just show you how it is fixed. Essentially, we have one single nut, the actual component itself, one single screw. Now this is an M3, I'm going to call it, being a 6mm component, I'm going to call it an M3 12mm screw going into an M3 30mm T-slot nut in this extrusion to fix it in place. Now, in this particular case, this arm here may need to be bent down so that it hits this nut here. As the gantry is moving upwards, you want this end stop to be depressed on whatever it interfaces with here, and it's usually this nut right here. So you may want to just bend it down. You should get about 580 millimeters of full Z clearance. It's a pretty simple component. There's a very short cable that joins this from here to here. I think it's easier than having it at the back. So there you go.
So the other thing that's worth mentioning, once you've pretty much set up your printer and you're ready to home for the first time, and by the way, when you are ready to home for the first time, I recommend you have your hand over this stop switch or this kill switch just in case something goes wrong. But one thing that you may notice is that, or really what you want is for this probe here to interface with the bed before anything else interfaces with anything else in the printer. Now, there is one culprit that I have noticed. It is this rear carriage may actually hit its I guess its endpoint prior to this probe, and really it probably won't hit. It'll probably hit a cable or something, and you'll hear the motor skip steps. If that occurs, turn it off straight away. Lift up the bed, and what I want you to do is just insert maybe 3 M5 10mm screws with 2020 hammer nuts across each of these extrusions, and that's just going to lift the bed up by maybe 5mm. And what that's going to cause is your probe to now interface with the bed prior to these carriers or gantry parts, components from interfacing with these lower Y extrusions. Okay, so I thought I'd just clarify the installation of and positioning of these filament out sensors. As you can see, they're just installed here along the extruder rail. Basically a stack of 2 with an M3, I think it's a 30mm screw going through to an M3 30 hammer nut. Now essentially what you're going to have, and I'll show you some photos to highlight this, so what we've got is a Bowden tube which couples into the top of each extruder, and then it just butts up, if you like, against the each respective filament out sensor, filament out sensor 1 and 2. So the idea being is that it does not need to actually couple to the filament out sensor, but the purpose of this tube is literally to stop the extruders from pulling themselves back towards the filament out sensors, because otherwise just the rotation of the extruder will literally cause it to literally travel along the filament back towards the filament out sensor. So for especially important for those of you who aren't using the active method, which you can see here. So if you just got rid of this motor, if you just want this to be passive, if you've got that Bowden tube, it really is probably what I would suggest just the easiest, simplest solution to the problem that we had. So now in the photos that you can see here, you can see basically how I have skewed each of them off in opposite directions. It doesn't really matter which direction they go, quite honestly. It's really a matter of aesthetics and personal preference. This is how I've done it. Essentially the tubes are long enough to get about 70% of the way across that rail, which is as far as that extruder carriage will ever travel. You can see in the photo here how they're just sort of butting up against the ends of the tubes. Are literally just butting up against the ends of the filament out sensors. And here's another view just to make things a little bit clearer. So if you have any questions about these ones, feel free to drop me an email or post a question in the forum. We'll talk to you soon. Thanks.